Monday, talking about exothermic, endothermic, and the relationships between the kinetic and the thermodynamic components. One of the things that I didn't mention, I know I mentioned it in the video though, was the correlation between the rate and the activation energy. I think I talked about it, but there's a correlation between the rate and activation energy, and then there's a correlation between the extent of reaction. And so the direction of equilibrium towards the product, extent of reaction, and the enthalpy, or delta H, right? So we talked about that, talked about delta G, how to calculate delta H, how to calculate delta G, and we even applied it to some examples that we were doing. So let's jump right back in, and we're gonna do the same thing on a couple of these other examples. And I can erase this because I actually have it saved already on Blackboard. All right, so let's do, and I'm gonna change the color on that pen right quick. All right, let's jump on this example right here. Don't you down me, you iPad. I'll slap you. All right, so tell me what's happening going from this example right here. Tell me what's happening going from left to right. Tell me what kind of reaction it is. And tell me how you would calculate delta H.
An elimination reaction.
Say that again.
Elimination.
Okay, I agree. Who was that?
Kristen.
Okay, I'm with you. How did you know that it's an elimination? That you're right.
Because it ends with a double bond.
The pi bond being formed in the product, right? Elimination always results in a pi bond, the formation of a pi bond. So you're absolutely right. All right. Now let's see how it happened. Let's put the arrows in, because part of the exercise is also learning how to push these arrows, right? For this elimination, there is not necessarily a nucleophile or an electrophile, right? So we don't have to label that, but we can label the leaving group in the elimination, because the elimination does have a leaving group. What do you think it is?
Is it the OCH3?
Yes, you're right. Y'all on fire today already, right? That's my leaving group. I'm going to abbreviate it as just LG. All right, you can see that over here because it left, right? It became a side product. Now, how did that happen? So now we know what the leaving group is. Let me put some electrons on that OCH3 on this side, so we'll know where to put the electrons from the elimination. So what's the first arrow that I need to draw for elimination? Is it here? Uh-oh. Is it there?
Yes.
Yeah. I want to make the pi bond, and in doing so, this carbon right here, remember, it can't have 5 bonds to it. So that's why I have to lose that leaving group, or kick off the leaving group, right? So here, boom, I lose the leaving group. Notice where the arrow starts. The arrow starts at the bond between oxygen, which is right here, and carbon, which is right here. So I'm breaking that bond between those two atoms, and I'm giving the electrons to oxygen. What kind of bond breaking is that? Anybody? We learned about 2 ways to break bonds and 2 ways to make bonds. If I break a bond, what's the suffix? Lytic or genic?
Lytic.
Lytic, right? And then if I break it and give both electrons in that bond to one atom, Is that hetero or homo?
Homo.
Hetero. Homo is
Two.
when each atom takes one electron. So this is heterolytic. Right? What about this one? Both electrons are coming from one atom to make a bond. So you know it's going to be genic because I'm making a bond. Think about creation, right? Genesis. So this is what? Help me out.
Heterogenic.
Heterogenic. Good. All right. We okay with that so far? So heterolytic is breaking a bond with two electrons leaving with one of the atoms in the bond. Heterogenic is making a bond with one atom supplying both electrons to make that bond. Right? The reason I'm saying that is because every bond is composed of two electrons. That's something that you can't forget. Every bond, every sigma bond, every pi bond is composed of two electrons being shared between two atoms. All right, it's a covalent bond. All right. So now let's figure out the delta H. What do we know? How do we calculate that?
Bonds broken minus bonds formed.
Good. Bonds broken minus bonds formed. What did we break?
A CO bond.
Mm-hmm. We broke a CO single bond, didn't we? And what did we make?
A CO double bond.
Good. So for the CO double bond, I bet you I erased it already. Or maybe not. Nope. 741 kilojoules per mole. For CO single bond, let's look at the chart. So again, I'm going to erase all this other stuff. I'm going to find carbon. Wrong pen, sorry. So I find carbon here and oxygen here, right? So it's 360 kilojoules or 86 kilocalories. And again, whatever you're working in, you have to make sure the units are the same. So 360 kilojoules per mole. So what is that? 381?
Yes.
Negative 381, right?
Yeah.
Negative 381 kilojoules per mole. Right? That is very highly exothermic. Oh, I gave it away. If it's negative, it's exothermic. Is that right?
Yes.
What does that mean in terms of delta, in terms of activation energy? Is it high or low?
Low.
Low.
Okay, good. What does it mean in terms of the Gibbs free energy? Is it negative or positive?
Negative. Negative.
Good. What does it mean in terms of KEQ? Greater than one?
Less than-
Okay, good. KEQ is greater than 1. Great. What does it mean in terms of, let me see, activation energy, Gibbs free energy, KEQ. There was one other thing that we looked at.
The chart.
Which chart?
It was fast or slow, the reaction.
Yeah,
Yeah.
well, that's the activation energy. So if it's a low activation energy, then it's going to be a fast reaction. Oh, it's whether it's endo or exothermic.
Exothermic.
It's exothermic, right? Because delta H is negative. I'm going to abbreviate that. What would the energy diagram look like for that reaction?
Reactant high.
The reactants will be higher in energy than the products. Is that right?
Yes.
So it looks something like that. Is that right? And then right here would be the transition state at the very top of that peak, or the peak of the graph. And then on the x-axis is time, y-axis is energy. Right? So let's look at that step. And let's look at the top, because that top reaction, can you see that reaction right here? Those two reactions kind of go hand in hand. The addition part first and then the elimination part. What's the overall delta H for that reaction? If the first step is 436 and the second step is minus 81, right? It's just the sum of the two delta H's. So what's the overall delta H? Is it 53? No, 55? Positive 55?
Yes.
Yeah, 436 and then minus 381. So it'll be positive 55 kilojoules per mole total for the total energy. All right. What that means is that that entire process going from ester to amide is about 50. It costs about 55 kilojoules per mole. Mainly because the CN bond that you broke is a little bit weaker than the CO sigma bond. Because the CO pi bond, you broke it, and then you made it again in the product. So, but it's the difference in the CO and CN bond. That's why it's overall endothermic overall, even though the first step is highly endothermic and the second step is highly exothermic. Overall, the reaction is endothermic. Does that make sense? Because again, the goal is to go from weaker bonds to stronger bonds, right? But you broke a CO sigma bond in the ester up top right here. And then you made a CN sigma bond down here. All right, so the top step is addition, the bottom step is elimination. All right, any questions? We're good so far? It's a lot easier working through the examples than it is just seeing it on paper or saying, hey, here, go do this. So let's do the next question. It's here, this one. We're gonna put the arrows in, we're gonna determine the type of reaction, and we're gonna calculate delta H and tell whether it's exo or endothermic. What do you think? First of all, and we need to label nucleophile and electrophile. Which one do you think is the electrophile? And you have the products over here. So don't consider all your evidence, right? So these are the products. What do you notice?
They switched.
Yeah, you're right. What got switched?
The NH2 and the Cl.
Okay, so the nitrogen displaced the chlorine, didn't it?
Yes.
So what does that make chlorine? It's a leaving group. That's exactly right. What kind of reaction is this if the nitrogen displaced the leaving group or displaced chlorine? What kind of reaction is it? Oh, it's a overall. It's a substitution, isn't it?
Yes.
Right? So nitrogen displaces chlorine. If chlorine is your leaving group, your leaving group is always attached to your electrophile. So this is the electrophile. That makes this the nucleophile. All right. And so how do I determine where the reaction happens within the electrophile? How do I determine that?
Polarization.
Look for the, very good. Look for the polarized bond. So we got a big time dipole here towards chlorine, right? So that means that the carbon is partially positive and the chlorine is partially negative. If you can grasp that, if you can grasp the polarization part, this becomes so easy because all of a sudden now you're just looking for where the reaction is going to happen. Anytime you're dealing with nucleophiles and electrophiles, what you're looking for is where is my polarized bond in the electrophile. And that way, once I find that, I know exactly where the nucleophile is going to attack, even if I don't have the products, right? Even if I don't have the products, I know that the nucleophile is going to attack at that partially positive carbon. All right. So let's put the arrows in. Having said that, which way is my arrow going to go? Is it going to go from nucleophile to electrophile or electrophile to nucleophile?
Nucleophile to electrophile.
Always, right? Always. Source to sink. Is the reason I can't draw an arrow from this carbon to nitrogen, right? If that carbon is partially positive. If it's partially positive, it does not have any electrons to give away, right? So I have to draw the arrow from the nucleophile to the electrophile, to the site in the electrophile that's going to react, right? So I start the arrow at the electrons, I end it on that carbon. And what type of arrow is that? Is it single or double-headed?
Double-headed.
Double-headed. Why? Because I'm moving a pair of electrons. I'm not moving one electron. Zoom in because I'm tripping. I'm not moving one electron. I'm moving two electrons. So both that lone pair on nitrogen is going to be used to make a sigma bond between nitrogen and carbon. Is everybody following that? We really got to be real clear about that, because one common mistake when dealing with electrophiles and nucleophiles, even in part 2, is the tendency to put the arrow just anywhere and point it anywhere, and you can't do that, right? You have to be very specific about where your electrons are flowing to and from. All right. Now, what else has to happen at that site?
The bond has to break to give chlorine the electrons.
Yeah, I got to break the chlorine carbon bond, right? That's my leaving group. And remember, the leaving group always, the leaving group always leaves with a pair of electrons, right? Because the leaving group is the more electronegative atom in that bond, sorry. I don't know what just happened. All right, here we go. So I got to break this carbon chlorine bond, right? Like so, boom. Notice where I started my arrow. My arrow starts at the bond, right? Because those electrons in that bond are leaving with chlorine. So I have to put the arrow there. And I end it on chlorine because chlorine is going to receive that pair of electrons. And if you look at the product, you can see that chlorine picked up an extra pair of electrons. I'm just going to highlight these because they're on the same side that chlorine, where chlorine was bonded to carbon. So it picked up an extra pair of electrons. And then also now I have a new bond between carbon and nitrogen, right? Very important. The reason we're doing this so meticulously is because there's another section coming up where we're going to have a lot of reactions that we're going to be doing. And if you can grasp the concept of nucleophiles and electrophiles, then when we do other reactions, it'll make more sense, because everything comes down to this, right? Everything is some type of nucleophile, electrophile, or acid-base interaction. unless it's radical. If it's polar, it's nucleophile, electrophile, or acid-base chemistry. All right. Any questions about that? So we know it's a substitution. We see the mechanism, how it happens. Now let's calculate delta H for this reaction. Let me see if I can move this. All right, so we know that's a substitution. What is delta H for this reaction? It's going to be the same equation, bonds broken minus bonds formed, right? And I always like to remember that like a bad report card, right? You got 3 B's and an F in a row. And so it's B, 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 F. Just always remember that, right? That helps you to know what to subtract from what. So the bond's broken. What did I break? I broke a
Yeah.
carbon chlorine bond, yes?
ACL.
Yes.
And then what did I make?
NC bond.
Yeah. Okay, good. Let's go down here to our chart. And again, we're going to read this from left to right. And this is in Blackboard, by the way. I think it's in the assignments folder. It's one of the things that's in there. It's also another little chart in there about the differences between nucleophiles and electrophiles too, right? So I broke a carbon chlorine, so I'm gonna highlight that. So here's carbon. I want to go down to chlorine, which is here. So that's 339. And then I made a carbon nitrogen bond, so I'm gonna highlight nitrogen in a different color. Right, that's the same color. Right, the carbon nitrogen bond is 305. Anybody not following how we're reading this chart?
I do have a question. What are the numbers on top?
It's different units. The top number is in kilocalories, and the bottom number is in kilojoules. I remember kilocalories. 1 kilojoule is. I'm sorry, 1 kilocalorie is 4.18 kilojoules. 4.184. So it's basically the top number multiplied by 4 to get kilojoules. You remember that from Chem?
Yeah, I just never seen it in a chart like this.
Yeah. So all that kilojoules and all that information, when you did calorimetry and calculating delta H, you can express the energy in kilocalories or kilojoules, or calories and joules, right? Because 4.184 joules is 1 calorie, like that. All right. So we got 339 for the carbon chlorine bond, and then 305 for carbon nitrogen. So let's go back up to our example and just put that in. So 339 minus 305 is plus 34. Is that right?
Yes.
Plus 34 kilojoules per mole. Right. So that means that this reaction is what? Exo or endothermic?
Endo.
Endothermic. Right. So we know if it's endothermic, then we can extrapolate all this other information, right? The
Yes.
activation energy is going to be higher. The delta G is also going to be positive. KEQ is going to be less than 1, right? All that we can take away from the delta H being positive. Yes or no?
Yes.
All right.
Yes.
All right. So once we figure out delta H, the other values become trivial, right? The other values become, oh, okay, if this is endothermic, all of these other things are also true, right? So but this is the easiest calculation that we can do, is to just find delta H, right? Because delta G double dagger, or the activation energy, you got to find that experimentally, right? All right, let's go and do, you just keep rolling. Is that all of those? No, we got one more down there, but this one doesn't have a product. I'm gonna cut it because I don't want to erase that, because when I post the notes, I'll leave that. Copy it. I'm gonna paste it on another page. Actually paste it right here.
Are those arrows already showing how the electrons and stuff are moving? And
Talking about on the last example.
yeah.
Yeah. You mad about that?
No.
How you gonna put the arrows in, bro? This is my job. No, I'm just joking. Yeah. Let me paste it, and then we're gonna talk about it. Because for that example, you didn't have a product. So I'll put the arrows in, and then you got to draw the product. And let me date that. This is 9/23. All right, so what's the product from that? And this, by the way, is a proton transfer, right? Or deprotonation. But the same principle applies in acid-base chemistry. The base is similar to a nucleophile. It's not necessarily a nucleophile. There's actually a big difference between the two. Well, it's a subtle difference, but there's a difference between a base and a nucleophile. So in this case, the OCH3 is acting as what?
A nucleophile.
Okay. But since it's attacking a proton, we're going to say that it's a base. I'm going to put / nucleophile, but it's not really acting as a nucleophile. But you're right. It's the arrows and the electron flow are similar to what a nucleophile would do. And then what does the other arrow, what does that indicate?
It's forming a bond.
The other arrow, the CH, the arrow right here on the CH bond, look where it stops. What is that telling me?
It's going to be a lone pair.
A lone pair. It's going to be a lone pair on that carbon. Who was that?
Taina.
Good. All right, so let me draw what we get. I don't want to paste the image. So that's what we're going to get from that. Plus HOCH3. But we can still calculate delta H, whether it's nucleophile, electrophile, acid base, doesn't matter. What did we break? We broke a CH bond, didn't we?
Yes.
And then we made an OH bond. Is that right?
Yes.
So then let's look at the chart, see what we got. CH is, we got to start at H. So we'll start up here. We'll go across to C. That's 414. And then we made an OH bond, so we can start at H and go over to O, and that's 464. Follow me?
Yes.
All right. So we'll put that in down here. CH was, what did I say, 414. And then 464. So what is the What's the delta H? Plus
Negative.
minus 50?
Yes.
Minus 50 kilojoules per mole. So that means that that is exothermic. Is that right?
Yes.
Okay, great. What else can you talk about? Low activation energy, negative delta G, KEQ being greater than 1, right? You can, all of that, again, information comes from the fact that we calculated delta H. Now let's go to the second part of that, because that's the proton transfer part. And then let's go down to here. Actually, I'm gonna see if I can. I'm gonna add a page right quick because I want to keep this together. Where am I? Here. All right. I'm gonna cut this one from down here and move it up so we can keep these together because these two are related. And then that way you can see them both. All right. So now let's look at this second reaction because they are related. And we're going to talk about what the overall reaction ends up being, right? What do you think? Help me out. How did I get from here to here?
Eliminate.
Yes. Who was that?
Demaya.
Good. I don't think, no, you said something before, but it was a long time ago. You're right. Elimination. It is an elimination. All right. So let's talk about the mechanism for elimination. Like, how does it happen? What do you think happened? We obviously lost chlorine, yeah?
Yes.
I got electrons everywhere, just all over the place. We lost chlorine. Let me put some electrons over here. Right? We lost chlorine. So we broke that CCl bond.
Did the lone pair above it move to make the second bond on the bottom?
It sure
Or
did. That's the only other place that we have electrons, right?
Yes.
Yeah. So I'm gonna take that lone pair and do this and turn that into a pi bond, which we've seen before, right? When we did resonance, you know you can take a lone pair and turn it into a pi bond, right? Is that okay?
Yes.
All right. So it's an elimination. We lost chlorine as our leaving group, and we formed a pi bond. So now, what is the delta H? What bonds did we break? Oh my gosh, you gotta be freaking kidding me. My iPad just died. That's all right. One monkey don't stop no show. What do we have? Now this is gonna be infinitely more sloppy because I'm writing with my mouse. Let me use my mouse pad instead. I had this iPad plugged in and everything. Just let me down. That's all right. We're gonna make it work. Add chlorine here and oxygen here. And then we eliminate it. Boom here. and then boom, like that, right? To end up with this. Plus Cl minus, is that right?
Yes.
And then we broke, actually type that. Broke a carbon chlorine bond. What was that? Was that 315 or 305? Say it was 305.
It was 339.
339? All right,
Yes.
I'm with you. And then for bonds formed, we made what? A C double bond, is that right?
Yes.
Now, I don't, let me take that back. I can find the chart because I emailed it to myself.
That one's 146.
140?
Wait.
That's too low. That's
No,
less than kilograms.
611. My bad. 611.
Okay, all right. So 611. Let me get back to the whiteboard. Can y'all still see the whiteboard?
Yes, sir.
Yes.
611. And this is in, keep in mind, kilojoules per mole. Now, we got to keep them units. Kilojoules per mole. I should start typing everything. This looks so nice. Don't look all crummy. All right. What is that?
Negative 272.
Okay. Negative 272 kilojoules per mole. All right. What was the first reaction, the deprotonation? What did we calculate for that?
Negative 381.
Negative 381.
Mm-hmm.
All right. So that step, because what I'm trying to show before my screen went out was that they were connected. First, you pull off the hydrogen, and then that pair of electrons that you leave behind forms a pi bond and forces out chlorine. So the whole overall process is an elimination. Are you following that? So you said negative 381?
Yes.
Wait.
It was that high?
Is that not the last one?
No, negative
Oh,
50.
50. Yeah.
Oh, yes. My bad. I'm thinking about the last one.
That's all right. At least you jumped up in there and said something.
Girl, you threw me for a loop.
Oh, my bad. You threw off the loop. My bad. Don't do that. Nah, we good. So this is negative 50 kilojoules per mole. What can we say about the overall process? Negative 50 and negative 272 ends up being what? Negative 322? Is that right?
Yes.
For both of those steps. Because see, what the point I'm trying to make is that the first reaction we did and this reaction are two steps of the same overall reaction. So it's a two-step process. So it ends up being 322 kilojoules per mole, right? So the whole process is highly, highly, highly exothermic, right? Highly exothermic. So if delta H for the whole thing is that, then you know that overall the activation energy is lower. The delta G is negative also. KEQ is greater than 1, so on and so forth. You can say that for each step because they're both exothermic, and you can say it for the overall reaction. All right. Any questions about that? Is this better? Anybody feel pretty good today on a Wednesday? A winning Wednesday.
Yes.
Yes.
All right. So that's the point, right? You don't want to leave out of class feeling like you just wasted an hour or 45 minutes or however long we spend together. So, but again, now what you need to do is keep practicing, right? That means that looking over. And I'll finish that problem once I get some juice in my iPad, a little bit more juice. I'm gonna finish that problem and post those notes, so you'll see everything we just did. But now it's up to you to practice and get more reps. We're gonna do. I think I have some more problems in this handout. We're gonna finish that back page, then we're gonna start on another page on Friday. Because I want to drive this home. Identify nucleophiles, pushing air. I got to drive all that home. So when we get to the next part, it's second nature, and you're not second guessing yourself. So because my iPad is dead and it's Wednesday, I'm gonna let y'all go to get y'all prayer on because Bible study night, today night, whatever. So I'm gonna let y'all go get some Bible study or something, or some lunch, or whatever you're gonna do. All right. Any
Okay, thank you.
Any questions about anything? Everybody feeling all right right now?
Yes.
All right. Is the pace working? Pace wise,
Yeah.
Yes.
are we on a good pace? All right. That's all I want to know. All right. So I'm gonna stop the video. I'm gonna stop recording.